Welcome back. Hope you're doing well. We are going to wrap up our unit here with regards to linear algebra with a big application for us here that's going to also not only be a culmination of this last unit, but be a good introduction for where we would like to end up at the end of our next unit as well. Remember that we're going to be talking about the advanced calculus take on calculus in these next coming weeks following our finishing of linear algebra. Namely, we're going to go through and do a more of a proof-based structure approach of the calculus sequence. So we're going to go through, take a look at continuity of functions and continue on all the way from Calc 1 through Calc 3, hitting the big points along the way. But quadratic forms are types of functions that we would like to analyze from a calculus point of view. What is a quadratic form? What are the things we can do with them, and how do they connect with both linear algebra and calculus? That's going to be the questions that we answer in today's presentation. Now, first things first, what is a quadratic form? A quadratic form is going to be a function of n variables, but of a particular type. You can notice that something's happening with each of these terms here. Namely, if you add up all of the degrees that in which all of the variables appear here, x1, x2 to xn, adding up all of those degrees always gets you the value 2. 2 exactly, not less than 2, not greater than 2, 2 exactly. So for example, terms like x to the 3, x to the 2 might appear, as could x to the 5 squared, as could x to the n, x to the n, whenever you get up to that point. But something that could not appear is x to the 1, or x1, x2, x3. None of these can appear as terms with coefficients in a quadratic form. Only those terms that when you add up all of their degrees together, what you end up getting is something with a sum of degrees looking like 2. So note that each term can be written in exactly that form. It's a constant times the powers of each of the x sub 1 through x sub n's, where the sum of the powers k sub I is exactly 2. Now, why are we making it so that these two things add up to be, these degrees add up to be exactly 2? Because there are other places where we can get these sorts of forms as well. And they are from equations, in terms of matrices, that look like this. Let's take x, for example, to be our generic x sub 1 through x sub n, all of our variables in terms of our Rn space. And let's let A be a sequence of coefficients here. Let's call them A11, A12, the entries here being indexed by row and then column. So A21 is the second row, first column entry. Now, every quadratic form can be written in exactly this way. X transpose times A times X. How is this working? You're taking a matrix x1 through xn, and you are writing that as a row vector. Then you are taking these aij, and then you're multiplying them times x1 down the way through xn. Well, if you multiply these two together, you're going to get one copy of some x. And if you multiply these together, you're going to get another copy of some x. And the copy of x that you get depends on, in case you're looking at this product first, the one of the matrix and then the column vector to its right, then that x power is going to be x sub j. It's going to correspond to the column that you find your entry aij in. That's going to be the particular row of elements that you're going to get here in this column vector. And then after that, once you look at this product with multiplying times x sub 1 through x sub n, this row vector on the left, the corresponding x variable that you're going to get multiplied on the left is going to be x sub I. So if you put all of this together, then you're always going to have terms of the form x sub ij, x sub I, x sub j. And if you continue to range what x sub I and x sub j can be, you're going to get all the way from 1 to n. You're going to get all the way there. So this is an example of a quadratic form. Let's see an example of this. Then f of x1, x sub 2, let's let it be 4 times x sub 1 squared plus 12 times x sub 1, x sub 2, plus 9x sub 2 squared. Should be a 2 right here. My apologies on that. Now what happens here? X of 2 squared. So we have each thing adding the powers together. If we look at each term, the powers add up to be 2, just like we would expect, 2 variables here. So in fact, everything has a constant in front of it. And notice that this 12x sub 1, x sub 2, we could have also written as 12x sub 2, x sub 1. We could have also written it in this form. Now that's interesting to us, right? Because how are we going to write this in terms of this matrix form? If that could be either maybe say the A12 matrix, the one that's associated to the term x of 1, x of 2, or it could be the coefficient of this one being x of 2, x of 1. And the answer is that there's actually a bunch of ways to do it. You can see here that I've paired apart 12x1, 12x2 into 2 times x1, x2 plus 10x2, x1, and written them into their corresponding matrix entries. And here you go. You've gotten this way of writing this quadratic form in terms of the matrix form x transpose times A times x. Now, I didn't have to do it with 10 and 2. I could have also done, or 2 and 10, I could have done it with 10 and 2 and switched those two things. I could have also done it where these two entries end up being equal. The one on the top right equaling the bottom left. You get 6 and 6 down here, and so you get 4, 6, 6, 9 as this matrix. Now, this is the form that we're going to see the most often because this matrix has a very particular form that we want to take advantage of. This is a symmetric matrix. So oftentimes we're going to have a choice of how to break apart two terms or two parts of a matrix that have the same arrangement of terms, namely x1, x2, and x2, x1. If we have 12 of x1 and x2, we're going to split it apart so that it's 6 and 6. 6x1, x2, and 6x2, x1, just like we did right down here. And that is because it's going to get us a symmetric matrix, which allows us to use some of the machinery that we've developed with symmetric matrices in the past. So given a matrix equation of the form x transpose AX, where XA is a symmetric matrix, where its transpose is itself, then we say that A is the coefficient matrix of the quadratic form. Now we're kind of distancing this from what we've been saying a coefficient matrix is for a change of basis. This is a coefficient matrix of the quadratic form. And a proposition is, and we've seen this here in some of our examples, is that every quadratic form is uniquely associated with its coefficient matrix. Everybody gets a coefficient matrix. We can always write something like that in this form. And if you ask for your matrix inside of there to be symmetric, well, then there's only one way to do it. There's only one way to split the x1, x2, the x2, x3 terms so that you get a symmetric matrix at the end of the day. So let's go back to that example and look at its coefficient matrix. We have 4, 6, 6, 9 as its coefficient matrix. We could do the same thing with the quadratic form x squared plus 2z squared minus xy and look at its coefficient matrix. And this one, recall, is now we have to think of x like as x1, z as an x3, and y as an x2, as it appears. Once we do that, remember that we're going to break up this minus xy into minus 1/2 xy, minus 1/2 yx. When we do that, we're going to get minus 1/2 on each of these entries for this coefficient matrix. Classical mechanics has a way of doing this as well. You may be familiar with the formula of kinetic energy, which is 1/2 mv squared. And if you have a more general notion of position coordinates, or if you have a kind of a more advanced way of discovering how velocity works, maybe it has more than just the degrees of freedom that we have in space, but other degrees of freedom as well, then whenever it has n degrees of freedom, then we can say the kinetic energy of this is 1/2 mass times the sum of the velocities squared, the velocities being taken in each direction. Velocities being taken with respect to like maybe an x direction or a y direction or a z direction or whatever other degrees of freedom are available given your scenario. So this is the form for kinetic energy, and this is also a quadratic form. Well, how is this a quadratic form? Well, if I go through and take a look at this, I have variables of the form dx1 dt, dx2 dt, all the way up to dxn dt. All of these are formulas, and if I square each of these, then I have a very particular matrix for this one. I have m over 2, m over 2, dot, 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 m over 2 as each of the diagonal entries of this matrix, and zeros elsewhere. This is an example of a quadratic form written in terms of its coefficient matrix. Okay. Had a couple of pauses here that I needed to go through to get to this matrix. There we go. So this gives us its coefficient matrix. So note that symmetric matrices, we're going to get to the nitty-gritty of how these symmetric matrices end up helping us out here, are orthogonally diagonalizable. We can basically break them apart using the fact that these can be written using an orthogonal, or in fact, even orthonormal if we wish, basis of eigenvectors. So we have the following proposition. Every real quadratic form, we've been calling them coefficient matrices of the quadratic form, but they can be reduced to a sum of squares of new variables with certain coefficients by a real non-singular linear transformation. What do we mean by this? That means that we can reduce quadratic forms to become diagonal. And that's because the symmetric matrix that we're looking at there, the coefficient matrix, we could diagonalize it. And the thing that gets us there is a linear transformation. It's going to be a change of variables. It's going to be its own coefficient matrix, this time for a change of basis. So let's see if we can view an example of this one. Let's take a quadratic form, and let's see if we can reduce this to look like a sum of squares. Now, we can use new variables here. We can do a change of basis. We can do a change of variables here. So let's see if we can write this q of x equals a squared plus 2ab plus 3b squared plus 4ac plus 6bc plus 3c squared as a sum of squares. Now, I have some squares already, a squared, 3b squared, and 3c squared. Right. So the thing is that I could write those if I wanted to, more specifically as squares, if I had written them as square root of 3b quantity squared and square root of 3c quantity squared. But that wouldn't really solve my problem right now. The issue is that I have a lot of these guys, 2ab, 4ac, 6bc, and I want those to become parts of new variables which are squares. And you might have some ideas about how to do that. What are some ways that I could pair these terms together to make this happen? Well, we wish to find this appropriate change of variables, and it wouldn't help to create more than the 3 variables that we already have. So we're going to also add a condition that whenever we try and write these sums of squares, we're going to make sure that the number of squares available are just 3. We want to be able to, when either combine all the like terms, we only have 3 terms at the end of the day. Or we could have fewer than 3 as well. That's also a likely, that's something that could happen. So here's what I'm going to do. I'm going to take a look at each of these terms, like a squared plus 2ab, and you may have already had the idea of thinking of this as completing the square, right? A squared plus 2ab are the first 2 terms of the formula for a plus b quantity squared. So it seems like that could be a useful type of tool. So maybe I'll take apart one of the b squareds from 3b squared and leave 2b squared over. But could I do more? I remember I have a third variable here as well. I have a squared plus 2ab plus b squared. Maybe I could add in a few more terms and make this a bigger square. Maybe that will help me get rid of a few more terms. So here's what I'm going to do. I notice that I have 4ac as well as some component for 6bc. And I'm going to take 4 of the bc. I'm going to take 4 of the ac. And I'm going to throw in some c squared here as well. And I'm going to write this expression. I have a squared plus 2ab plus b squared plus 4ac plus 4c squared plus 4bc. The question is, what happens when I multiply all of these things together? It may not be immediate as we begin with, but this is actually a plus b plus 2c squared when it's all combined and put together. So there is a way for us to be combining these in ways that are a little bit creative. Okay, so because we have more than 2 variables here, we have 3, there are unique and creative ways for us to be trying to combine these terms together, like a plus b plus 2c quantity squared. And we can keep going here. We can take this process, combine this to be a plus b plus 2c squared, and then this is what we're left with. The only thing that we really need to deal with now, we've got a square, we've got a square. We could try and deal with this 2bc as well. And if I do that, then I can take apart one of these b squareds, add a c squared here to get that this is b plus c quantity squared. Now, at this point, I have written q of x in terms of a sum of squares. However, it is a sum of 4 squares, which is just too much information to work with. I don't want to work with 4 variables when I could be working with 3. But this is not the only way we could have separated this. We could have taken these last 3 terms, and instead of doing the thing of trying to complete the square with this 2bc to get rid of it, we could have instead written this like this. We could have written this as c squared, this c squared, minus 2bc plus b squared, and then just put a minus in front of it. That would have gotten rid of these 2 terms, and written this as what? Something like c minus b quantity squared. Then returning just past the first line and connecting all of these things together, this 2b squared becomes 3b squared. And then we get that q of x equals this. And that's a way to write this in terms of 3 terms, each of which is its own sum of squares. So for example, if we write a tilde to be a plus b plus 2c, so that's like our first variable here. B is c minus b, and then c tilde, in order to write 3b squared as a square, I need to write b square root of 3. Then I get q of x equals a tilde squared minus b tilde squared plus c tilde squared. So now we have written this q of x in terms of a sum of squares. And we've done it here using these combinations of coefficients. But here's the question. Here's the age-old question that we're always kind of curious about when it comes to math. And the question is this. Oop, didn't put it on here. In fact, I have a little bit more to before I say that, so forgive me. I'll go ahead and say the question because I was going to say it anyway. The question was going to be, can we do better? Is there a way to write this in terms of, instead of 3 variables, is it possible to write this in terms of 2? But before we get into that question, let's connect this change of variables back into our way of writing in terms of a coordinate matrix. So we've got our way of writing a tilde, b tilde, and c tilde here in terms of each of their individual variables. Well, what's the change of basis in terms of the change of variables that's going on when we write these new variables here? Well, we can separate each of these apart based on the fact that, for example, 1, 0, 0, if I write that here, isolate all of the a terms, then I'm going to get 1, 0, 0 for this first column, and then the b terms gives me 1, negative 1 square root of 3, and then the c terms gives me 2, 1, and 0. This is going to give me a coordinate matrix for a change of variables that I could go through and write. So now I have my change of variables, and I could write my diagonal matrix as well. My diagonal matrix would be 1, negative 1, and 1 with respect to this change of variables. Because if I go through and write this, then I'm going to have x transpose on the left, x on the right, and everything would multiply neatly. So now there's our question of, can we do better? Could we have done fewer than 3 variables with this? Now, the principal axis theorem is useful for us here. It essentially is telling us something that we know already. Let's say that you have q of x being an arbitrary quadratic form. Then there is a real orthogonal matrix S such that you can write q of x as your sum of squares. That is, you could write this in terms of your little diagonal matrix filled with lambda 1 through lambda n, where these are the eigenvalues of your matrix A, since A is symmetric. Now, the orthogonal matrix S that we're looking at, that's our unitary matrix in terms of complex variables. But since we're in the real space, this is an orthogonal matrix, and this is our change of basis matrix. This is our coordinate matrix. We'll take a look at this as S transpose now, because usually whenever we write our change of basis, we look at x equals S times x tilde as our way of writing these change of variables formulas. At least that helps us be consistent with what we were discussing prior. Now, so the proof of this is going to be pretty nice because it's going to connect back to the notion that A is symmetric. And in fact, since Q of X is this X transpose AX, we may recall that this is related to how the inner product works on these finite dimensional vector spaces once we write them in terms of coordinate matrices on Rn. Well, in particular, we're taking a dot product. This is AX dot product with the vector X when we write it this way. So we get a matrix like this. And since A is symmetric, we can diagonalize it so that S transpose AS is equal to the diagonal matrix D. So let's define X tilde to be S transpose of X. What's going to happen then? X is going to be equal to S times the tilde of X. That's what we had up on the previous page before. Well, how is that going to change AX comma X? Well, now we can write that X is SX tilde if we're trying to do our change of variables, for example. And so we could write SX tilde right here. And we can also write S right here. In fact, S should be written right there. That's a little bit of a typo. So this X becomes SX tilde as well. And I can bring that S back over here by taking the adjoint or the transpose of this matrix, bring it back over here to the first argument from the second argument. And now I have S transpose AS, which is now writing this in terms of a diagonal matrix, but in terms of my new variables. Since D is diagonal, expanding this inner product yields only terms of the form A x sub I tilde squared, because now this is a diagonal matrix. If I wanted to take a dot product of things like this, I'm going to have lambda I times x sub I tilde. And then taking the dot product of this with vectors of the form x sub I tilde. When I take this dot product, remember all of our entries are going to stay the same when we multiply these together. So we're going to get lambda I x sub I tilde squared. So this kind of is our little bit of a proof of this principal axes theorem. Namely, we didn't just have to work in terms of the previous example to do this. The principal axes theorem gives us a solid way of making this happen. We just know that there exists a change of variables. But that change of variables can come from the diagonalization argument that we were working with in our previous presentation. We can make our orthogonal matrix S here our change of basis matrix. We can make lambda 1 through lambda n our eigenvalues of the matrix A being the coefficient matrix of this quadratic form. Let's go ahead and put all of that together here in this example. And let's take a look and notice that maybe it's not the nicest thing that we were ever expecting. But for example, here is the symmetric matrix of this change of this quadratic form that we were looking at before. So this quadratic form had this as its matrix, its symmetric matrix, its coefficient matrix. Once I go through and write all of this down, I can see that these are the right entries, and I can also see that this is symmetric, and I could go through and calculate its eigenvalues. Now, this was certainly done using Wolfram alpha because you can take a look to see what these eigenvalues are and notice that they are not the nicest eigenvalues in the world. These are not ones that calculate out to be extremely nice. At least they don't. If we had gone through and had cube, we could have had cube roots or square roots and somewhere in our answer perhaps. But when we approximate them as decimals, they are not whole numbers, they're not fractional numbers. They are definitely something a little bit wonky. The corresponding eigenvectors, also calculated using Wolfram alpha, also do not look very nice. But if we needed to, we could use these values to immediately, thanks to the diagonalization, binds the eigenvalues and eigenvectors that we're working with. So once we have all of this, we can write q of x as lambda 1. This is our eigenvalue, lambda 1, and x tilde of 1, where this is the corresponding eigenvector. So I could have just plugged this in right here and taken that coordinate to be squared, x of 1 tilde squared for that in terms of how this looks in terms of our 3. All right. So this looks like a different answer because diagonalizing gives us an orthogonal basis of eigenvectors, okay? So to be more specific here, because I'm not as specific here in these slides as I need to be, what I'm saying here by saying x of k here is the corresponding eigenvector, what I'm saying is this: x of 1 tilde is going to be equal to something like this, 0.505486 times the original vector, the original variable, x1, or in this case, a, plus 0.925528b plus c. So this is all of this stuff squared. So this is what's being mentioned here. We can write this indeed as a sum of squares, but as you see, the squares, the entries of them are not necessarily nice, but at least now we know that it is possible. What's more, we know that this is an orthogonal basis of the rank space of this matrix, and so if this had been possible to do in fewer entries, right, then we would have been able to, thanks to diagonalization, shave off one of our entries here, thanks to how that orthonormality sort of stuff works. So we know that we have actually gotten the best possible, that 3 variables is the best that we could do. All right. Now let's keep going here and look at this in terms of what if we had 2 different ways to write these 2 equations. Now, we've just seen that it's possible to write, for example, the previous example, we had a way to write it as a sum of squares in one way, and to write it as a sum of squares using 3 terms in another way. 2 very different ways, with 2 different changes of variables and 2 different sets of coefficients out in front of them. So this is exactly what the Sylvester's theorem, or the law of inertia for quadratic forms, begins with. Let's say that you could write this quadratic form in 2 ways, terms of different sums of squares. Then something that is always going to be true is this: the number of values in a sub I that are positive is the same number of values in b sub I that are positive. That the coefficients out front, the number of which that are positive in either way of writing this quadratic form as the sum of squares, is the same. Let's check that. In our previous way of writing it, in terms of the eigenvalues generated from Wolfram alpha, we see that there are 2 positive eigenvalues and 1 negative eigenvalue. And if we go back to our previous way of doing it, whenever we wrote these eigenvalues out front, not eigenvalues anymore, actually, but instead the coefficients of this quadratic form, once written as a sum of squares, we had 2 1s, positive, and 1 negative 1, a negative. So the same number of coefficients went out front here for this quadratic form. The same number, 2 were positive and 1 was negative. So note from our previous example, indeed, we had 2 positive and 1 negative value. So this is true regardless of however many different ways we could have found such a sum for these examples. So let's keep kind of going here. Let's orthogonally diagonalize the quadratic form with this coefficient matrix of A. Now, orthogonally diagonalize means let's use our second method rather than our first method. Our first method was a little bit more guess and check. Let's go through and try and find an orthogonal basis for this and try and move forward based off of that. Well, at this point, we've gotten a little bit more comfortable with trying to find eigenvalues and eigenvectors for each of these. So I'll go ahead and just show off what these are here. We find two eigenvalues of this matrix, 9 and 4, respectively, with eigenvectors 1 square root of 5 over 2 square root of 5 and negative 2 square root of 5 over 1 square root of 5. So what that means is this. The quadratic form that we have written here, which is 5x1 squared plus 2 plus 2, 4x1, x2 plus 8x2 squared, can be written as a sum of squares in the following way. 9 times x1 squared plus 4 times x2 tilde squared, where x1 is 1 over square root of 5, x1 plus 2x2, and x2 tilde is 1 over square root of 5, negative 2x1 plus x2. Now, so that's the way to write q of x here. And I could go ahead and bring out the square root of 5s if I would like, or if I want to write the coefficients as being inside the parentheses, I could do that as well. I could have written that as 3x1 tilde squared plus 2x2 tilde squared if I truly wanted to write this as a sum of squares. So there's a couple different ways to write this through here, depending on how nice we want our values to look. Now, how can we graph these quadratic forms? And this might seem like a strange question. So far, what we know about quadratic forms is very algebraic. Namely, we can express them in two ways. One as a particular, kind of like a multi-polynomial, if you will, with a lot of different variables, perhaps. Or we can write it in terms of a matrix equation. But it turns out we can be graphing these as well, and that either of these forms can be useful in helping us graph what these things look like. In particular, what we're going to do is we're going to set our quadratic forms equal to something. You're going to see here in this example, we're going to set a quadratic form, like this guy, equal to 1. And we're going to ask the question, what does this look like? And what we're going to see is that this is going to look like a conic section. Let's go through and see how we would do this. Let's consider the second degree equation, 7x squared plus 2 square root of 3xy plus 5y squared, which is equal to 1. We're setting that quadratic form equal to 1. Let's get its coefficient matrix. Let's find its eigenvalues. Let's find its eigenvectors, and let's put them all together. Then what ends up happening is that we get an equation that looks like this. If we use x tilde squared and y tilde squared, again, writing them in terms of x tilde being like negative square root of 3 over 3x plus y, and y tilde being square root of 3x plus y, then we get this equation right here, which we may remember as an ellipse, with a major axis in the direction of the first vector, the eigenvector v1, and a minor axis in the direction of v2. So this is telling us the directions in which these two things are going in. After we apply this change of variables, instead of going in terms of x and y, which is how we would normally have our ellipses be drawn, if instead we were going in terms of x tilde and y tilde, what's happening is that we are doing a change of basis as well. 1, 0 is now becoming negative square root of 3, 3, and 1. So it's going off in this direction. And then the vector 0, 1, v2, is now becoming square root of 3, 1. Square root of 3, 1, of course, going off in this direction. So what's going to happen here is we're going to get an ellipse. Since these two things are orthogonal to each other, we still get something that looks a lot like an ellipse whenever we go through and graph it. But notice that this ellipse isn't centered so that its major and or minor axes are on the x or y axis respectively. This can be off kilter. It could have changed its direction of the major axis. In particular, the major axis here for V1, we know this ends up being the major axis because the smaller number here is out here in front being multiplied times it. So x tilde gets to be a little bit bigger in order for us to get to 1 with this term. So this gives us that the major axis is in the direction of plus or minus V1. So we can keep going. We can graph these quadratic forms given by these coefficient matrices. Let's graph the one given by 3, 2, 2, 6. And let's see how this sort of thing looks. We start by going through finding its orthonormal matrix of eigenvectors, perhaps. Here are the eigenvectors that we had from before, or not, rather, this is a slightly new example. So we go through and find those eigenvectors again, although they are similar to a previous example. So we have eigenvector 1, eigenvector 2, each one becoming the column of this matrix of eigenvectors. So we can think of S as like our coordinate matrix here. And the corresponding eigenvalues for these are 2 and 7, respectively. So if we set y to be equal to S transpose of X, so this one is y1 and y2, for X is, of course, x1 and x2, then we get this equation, 2y1 squared plus 7y2 squared equals 40. Now the question is, where did 40 come from? And the answer is that I forgot it. I had to pause and write something extra on the slide. My apologies on this. For the rest of the slide, let's read the example like this. Let's graph the quadratic form given by the coefficient matrix A equals 3, 2, 2, 6, and the equation X transpose AX equals 40. So 40 is where that thing came from. That allows us to set everything here into an equation. And we notice here, once again, that's the system that we get here working with y1 and y2 gives us an ellipse once again. Now, the ellipse, again, is going to work in terms of y1 and y2. That's going to be, well, if we're looking at this, we're going to be looking at, let's check things here. We're going to have to taking the transpose of this matrix in order to figure out how y works in terms of this. So if we're taking these pictures, then we should get that, for example, S of E1, the first vector here, is going to give us V1, if I had plugged in 1, 0 here. So if I'm applying this change of matrix to things inside of S, of X, it's going to give us something in terms of E or a V instead. So our first matrix is going to be going off in the direction of 2 square root of 5 and negative 1 square root of 5. So we're going to have this as our first place for this to go, and that's going to be graphed to go off in this direction. So this is going to be our major axis here, since this is associated to y1. And then our minor axis is going to be going in the direction of 1 square root of 5, 2 square root of 5. So it's going to be going off a little bit like this. And that's going to be where our minor axis lies. If I were to just quickly graph what this matrix would look like, then I would get an ellipse that looks a little bit like this. So this would be my graph for this quadratic form given right here. All right, now there's different types of quadratic forms here as well. We've seen how we can graph these quadratic forms and make them look like specific things if we set them into equations. But quadratic forms have other specific qualities. And one of these terms here, I mistakenly went ahead and referred to, I think back last week when I was talking about adjoints, that there was a specific type of adjoint known as a positive definite one. Now, positive definite is not something we had talked about before this, but now we get to talk about what positive definite actually is. So here we get to bring back that definition. We will say a quadratic form Q is positive definite if Q of X is greater than 0 for all non-zero X in the n-dimensional vectors. So what does that mean? Q of X, that is, whenever I plug in values like x1 squared plus x2 squared, for example, if that's Q of X, I ever plug in values here, as long as the vector that I plug in is not the 0 vector, then anything that I plug in here is going to be greater than 0 because x1 is greater than 0, x2 is greater than 0, and so on and so forth. Now we're going to say that the form Q is negative definite whenever Q of X is less than 0, something like maybe negative x1 squared minus x2 squared. So here we have positive definite versus negative definite. So these are two examples of these sorts of quadratic forms. And a quadratic form, if it takes on both positive and negative values, maybe something like x1 squared minus x2 squared, then this one is going to be indefinite. Because sometimes it is positive and sometimes it is negative. It just depends on what non-zero vectors you are plugging in there. Now, this needs to be true for all vectors that you plug in here, both ones that are positive and ones that are negative. All non-zero x in Rn. Here's a couple of other examples. x1 squared plus 5x2 squared, and then x1 squared minus negative x1 squared minus 5x2 squared is less than 0, and then x1 squared minus x2 squared, the same example that we had from before. Now, there's a way to be able to determine how quadratic forms work in terms of their eigenvalues. And this might make sense to us based on the fact that we can diagonalize these quadratic forms in the following way. We can write q of x in terms of a sum of squares, lambda 1 x1 tilde squared plus lambda n xn tilde squared, where lambda 1 through lambda n are the eigenvalues. And indeed, this is going to connect these pieces of the puzzle here. If q of x is positive definite, that means whenever I plug in a non-zero thing, all of these xn's, x1 through xn tilde squareds are all going to be positive. So what actually determines if q of x is going to be positive or not is the values of lambda 1 through lambda n. Indeed, if lambda 1 through lambda n are all positive, this ends up being a positive definite form. And if they're all negative, then this ends up being a negative definite form. So that's going to kind of be our connecting piece of the puzzle here in the proof that you see here. The other hand, q is greater than 0. So the idea is we have to kind of be able to go back and forth. I've shown the one if eigenvalues are positive, then q is greater than 0. On the other hand, if q is greater than 0, then if we give its basis of eigenvectors vi and calculate the eigenvalues for it, which we can since this is a symmetric matrix, then we can calculate that each lambda sub I, which is really just q of v sub I, that's because v sub I is an eigenvector. So if I just plug in what q of v sub I gives me, then it's going to be just lambda I. And if I go through and calculate that, then what I get is going to be, well, this is already v sub I is a element inside of Rn, so I can plug that in for q and get out the value lambda sub I. And because that happens, I'm going to get something that's greater than 0, right? So that's going to give me this. By the way, the reason that these two things are equal is that, remember, these are written in terms of the change of basis, where the eigenvectors form the standard, the orthonormal basis in terms of this change of basis. So we're really just looking at the matrix of vectors like this, where there's a 1 in the ith position. So if I plug in the 1 in the tilde x sub I position, then what I get out of q sub x is just going to be lambda sub I. Thanks of that. Now, the proof for negative definite quadratic forms are similar, and because that's similar, the indefinite follows right alongside it. It's kind of like the middle ground for both of those cases, and since those things are also if and only if. Our previous example, the one where we had solved two different ways, is an indefinite quadratic form, for example, and we can count because it had two positive eigenvalues and one negative one. Now, is there an easier way to determine this? Notion of positive definite and positive definite or negative definite without having to go through and find the eigenvalues? It turns out that the answer is yes. We can do this by looking at the leading principal submatrices of the coefficient matrix for this quadratic form. Leading principal submatrices are this. You start by looking in the top left corner of your matrix, A11, and you look to ask about A1, and you go through, and we're about to take its determinant. But then you continue going on and looking at other matrices, this one, a 2 by 2, taking the top 2 by 2 matrix in that form. And you can continue this process all the way down to AN1, A1N, and ANN, right down through here. And if you do this, then you're going to be able to see that you can get different principal leading submatrices by just kind of dividing them up into k by k submatrices, all in the top left box. So A sub k is going to be the case of k times k submatrix formed, should be ED there, by the first k rows and k columns of A. And then finally, A sub n needs to be A. That is also a leading principal submatrix. All matrices have themselves as one of their submatrices. So the one way of seeing this is a theorem that says that the quadratic form x transpose AX is going to be positive definite if and only if, again, A has to be written in symmetric form, the leading principal submatrices all have positive determinant. But that is one way that we can use to find out this notion of positive definite if we aren't going to go through and find all the eigenvalues for this. We know, for example, that when it comes to larger and larger matrices, that it is harder to find eigenvalues than it is determinants. Determinants can be brought down using minor using the minor matrices, determine it by minors, things like this. However, that is not always that is much easier to do, uh, usually than trying to find the eigenvalues for some of those larger matrices. And the corollary theorem holds for negative definite as well. If your determinants are all negative for your leading principal submatrices, you also get that particular form for your quadratic form, and that's going to be negative definite. Of course, if your determinants are some positive, some negative, you do not fall in either of these categories, and hence you are an indefinite quadratic form. Now, where all of this connects to, and where we're starting to see some of this calculus connection here, is by finding maxima and minima of multivariable functions. Now, in Calc 3, we focused more on the function of two-variable case because it's easy to picture. We have a picture right here of what those max and mins look like. We can find absolute max, absolute min, and local max and local min by using a particular type of theory that will also encapsulate a little bit in what we're discussing today. So recall that the maximum is going to be a point x, y, z in terms of like a two-dimensional or a two-variable function, such that the last coordinate, we would say the z coordinate, if we were looking at x, y, z, the z coordinate is bigger than anything else around it in a neighborhood. That means in anything close by it. If we look at this point and look at all the points around it, this is the biggest point that's there. Similarly, this is a local maximum. It's similarly that way in a neighborhood. And this one's also a local maximum. So these are local and absolute maximums that are down here. The minimum, similarly, can be done using just by flipping this sign right here. Instead of looking at greater than or equal to, we could be looking at less than or equal to for that definition. Now, we could do the same sort of definition now, not only for functions of two variables, we could do it for 3, 4, 5, and so on and so forth variables. And one way to find these maxima and minima was to find derivatives. In Calculus 1, when we had single derivative functions, what we would do is we would apply first and second derivative tests to find where maxima and minima are. And similarly, whenever we were looking in terms of two variable functions, we would do a similar thing, but we would have our own special second derivative test. Namely, we would form something called the Hessian of that function. You may or may not have been familiar with that term, but that is the matrix that we form whenever we took the second derivatives of this function and put them together into a matrix. So at the end of the day, we know for sure that derivatives are very useful in determining max and min. These derivatives altogether could be compiled into a Taylor series, which is something that we may have discussed in Calc 2. And remember that the way that we would formulate these Taylor series is we would say, okay, let's center at a point x. So we're going to try and find the difference between f of x at plus h, some small difference between x and the value we're looking for. And we're going to differentiate that from the value that the function gives us at x. Well, how could we do that? If we just look at what we have over here, that is, if we kind of cross this stuff out, excuse me, one more time. We cross this stuff out, you might look at this and realize that this is actually the linear approximation of a function, right? So there's a little bit of mx plus b going on here, the slope of the tangent line, times our variable that we're changing, in this case it's h, plus something that involves going through and taking the y-intercept, in which case this would be b if we're looking in terms of x. So there's a little bit of a linear approximation going on here, but we could add this to be a quadratic approximation, a cubic approximation, a quartic approximation, using all of these Taylor polynomials. And in general, if we have a smooth function, one in which infinitely many derivatives can be taken, then we can actually get that these two sides equal if we're allowed to take this series and add it to be and see where it converges its limit. Now, a Taylor expansion can also be formed for functions of several variables. We only have to think about the fact that we can make small changes with respect to either variable, x or y, with this function. And if we do that, then we're also going to be taking partial derivatives with respect to x and y. It may not be, hopefully, too surprising that when we take the first derivative here, if we are going to be changing with respect to x, and we're going to pick up changes with respect to x, we want to multiply it times how much we're changing in the x direction. We're going to multiply it times h. And similarly, in the second term, if we're looking at a change in y, then we're going to be multiplying that change in y times how much we're changing in y to figure out how much our z coordinate changes. And then we could do the same thing for the quartic, or rather for the quadratic approximation term, this one that has h squared, 2hk, and k squared in it. By the way, you may notice that this is a quadratic form in here, where our coefficients are given by these second derivatives. And then h squared, h2hk, and k squared are each on their own different kinds of variables that we could be plugging in for a specific type of function. So to find critical points of this function, what we did in multivariable calculus in Calc 3 was that we set our first and second derivative, or our first partial derivatives equal to 0. Once we set our partial derivatives equal to 0, what we would do after that is we would say, okay, let us form the following matrix. We would look at f of xx, f of xy, f of yx, but that's the same as f of xy thanks to Clairaut's theorem, and then f of yy. And we would say, let's find out what happens with this matrix. We would talk about the determinant of this matrix, and if it's greater or less than 0, that would give us a min or a max respectively. So we have this sort of formula to be going through here. Now, the expression here in the proof of why this actually works is playing a key role. It's h squared f sub xx plus 2hk f sub xy plus k squared f sub yy. This ends up playing a key role here. Again, a tilde, b tilde is our critical point of this function. So notice that if we form the vector xhk, then indeed this matrix here is a quadratic form. This is giving us a quadratic form for this matrix. And that's why this matrix ends up playing such a big role. The notion of a Taylor expansion can also work in terms of 3 dimensions. Once we go through and maybe make for our x, y, and z coordinates a h, k, and l change respectively, then we can make this quadratic form using now all of the second mixed partial derivatives arranged in this particular form. This is a Hessian of the function f. And that is true for the previous slides one as well. That was for a function of 2 variables. This one's for a function of 3 variables. So we can continue to get quadratic forms by isolating the second degree term of the Taylor series for this particular function. So let's go ahead and use this in an example. Let's take a look and find the local maximum values of x cubed plus y cubed minus 3x minus 12y plus 20. Let's see if we can find the maximum values for this. Well, the first thing we want to do is find critical points. When we did this in multivariable calculus, we would take our first partial derivatives and set those equal to 0. When we do that, we're going to get 4 critical points: 1, 2, negative 1, 2, 1, negative 2, and negative 1, negative 2. So that gets us our critical points for this function. The second derivatives also form very nice values. The second derivative of x, where the first derivative is 3x squared minus 3. Taking a derivative of that with respect to x is going to give us 6x. Taking a derivative of f sub y with respect to y is going to give us 6y. Notice that taking either derivative, x or y, with respect to the opposite variable is going to give us 0. So we can form the Hessian of this matrix, where each of these functions are evaluated at the critical points. So for example, we could start at 1, 2. And we could just plug in x equals 1, y equals 2 for each of these second derivatives. If we do that for f sub xx, we're just going to get 6 times 1. That's going to give us 6. If we do f sub yy, that's going to give us 6 times 2. That's going to give us 12. And then, of course, f sub xy and f sub yx are both 0, giving us these entries. Now, A is a diagonal matrix. That's our favorite thing. And we can see that its eigenvalues are 6 and 12. So let's talk about back again the fact that this is a quadratic form. Its eigenvalues are 6 and 12. What does that tell us about the quadratic form? If its eigenvalues are all positive, this is a positive definite form. Well, what does this mean about the quadratic form that is given like this? F of 1 plus h, comma, 2 plus k. What happens if I plug in a non-zero vector for h and k? Well, if I plug in a vector for h and k that is non-zero, then what's happening is in the function, what I'm doing is I'm making a small change away from the point 1, 2. I'm changing it a little bit. But the function value we know is going to be greater than 0, right? This change going from plus h and plus k, this is going to be a positive change because this quadratic form is going to be greater than 0. That is f of 1 plus h, comma, 2 plus k is going to be greater than whatever happens if we plug in 0 for each of these things. If we had plugged in 0 for each of these, oops, if I plugged in 1 plus 0 here, as well as, got to find it again, give me a second. Thank you. So 1 plus 0 here, as well as 2 plus 0 here, this would be when the q of x is equal to 0. And here we know that this is greater than 0 because this value, this q of x, is going to be when I'm plugging in a non-zero vector in for h and k. What that means is that this is bigger than this. That means that we increased. And in fact, we increased regardless of what non-zero vector we plugged in for h and k, because this quadratic form is positive definite. So any change from this point gives us a bigger value. So that means that what we get is a local minimum of this function. If we plug in f of 1, 2 into the function that we had originally, we would get the z value of 2, and that is going to be a local minimum. And we can continue this process all the way through. We can find Hessians for example, at -1, -2, giving us this matrix right here. And we notice that it's already a diagonal matrix where its eigenvalues are negative. In this case, anytime that I plug in a non-zero vector in for h and k, again, notice that now my function is centered at -1 and -2. Any change on this is going to make a negative change. If I plugged in 0 and 0 here, I'd have a q of a 0 vector, which gives me 0. And I know that 0 is greater than what happens when I plug in any non-zero vector in for here. And that non-zero vector is going to give me -1 plus h, -2 plus k. So any small change is going to make it less than whatever happens at f of -1, -2. What does that mean? Not that it's a local minimum like I mistakenly wrote here, and I'll do it in a different color to make sure that it is clear. It's going to make it a local maximum instead. It's going to be a local maximum because any change is going to make the number smaller. It's going to make this number smaller than the number it was originally. So this will become a local maximum. And then finally, if I go through and find the Hessians of these other ones, I'm going to get matrices like 6, 0, 0, -12, and -6, 0, 0, 12. Notice that these are eigenvalues that are mixed, positive and negative. This is when the Hessian shows that the quadratic form is indefinite. So that means that these are saddle points of the functions. In some points, some directions they grow, and some directions they shrink. Sometimes the quadratic form is positive, sometimes it is negative. Let's go ahead and do one more example here to classify critical points for 2x squared plus y squared plus 11z squared minus 2xy plus 4xz minus 6yz minus 2y plus 8z. Woo! Okay. Notice in particular, we did not deal with this in some Calc 3 courses because this is a function of 3 variables, f of x, y, z. But now we can classify this thanks to how powerful quadratic forms ends up being. First, we're going to go through and try and figure out where are the first partial derivatives equal to 0? Where are our critical points? Here we've got a system of equations we can go through and solve, and we know that we can use the augmenting matrix form and use Gauss-Jordan elimination to try and figure out what x, y, and z are. Once we go through, we find there is one critical point, namely 1, 2, and 0. After I do this, I'm going to go through and start taking second partial derivatives. I'm going to get these values, derivatives of 4, 2, 22, -2, 4, -6, all written in these sorts of forms. And then if I go back to that formula on that previous slide that I had for how I plug everything in for the Hessian, then this is the formula that I get. I get 4, -2, 4, -2, 2, -6, 4, -6, and 22. Notice that I had to repeat some values. I had to repeat values for f sub xy, for example, because that's also f sub yx. -6 and -6, 4 and 4. All of these are repeated values. Notice that this makes the matrix symmetric. Question, is A positive definite? Well, we can use the principal submatrices to help find out. Of course, we can go through and find the characteristic polynomial, but like we mentioned, for bigger matrices, it's often more helpful to try and just find determinants of smaller matrices. The determinant of 4, for example, that's our first principal submatrix for this, and that's going to give us determinant of 4, which is greater than 0. Then we can find the determinant of 4, -2, -2, 2. That is going to be for this matrix right here. That's going to give us a determinant of 4, which is greater than 0. And after we do the determinant of the entire matrix A, that's also going to be greater than 0. Well, that means we have a positive definite form. So just like we saw in our previous example, that's going to give us a minimum of this function. So that's going to do it for me today. We've learned a lot about how quadratic forms can help us tie the bridge together between linear algebra and calculus, especially multivariable calculus, because whenever we are talking about multiple variables moving at the same time, often they're moving linearly, especially when derivatives are involved, since we know the derivative is a linear operator. Thanks to this sort of stuff, we can connect these two things together, matrix algebra, linear algebra, and calculus. And so that's what we're going to get to be talking about in future weeks, is this notion of calculus. But here we learned about quadratic forms. We learned about the terms of positive definite, negative definite, our ways of classifying these things. And at the end of the day, how to write these quadratic forms as sums of squares, because that's a useful way for us to figure out how these eigenvalues and eigenvectors work together with the symmetric matrices. But that'll do it for me today. Thank you so much. Have a wonderful day.